Hi, and welcome to the Calculus 3 tutor, and in this section we're going to continue talking about the concept that we started talking about several sections ago, which was the partial derivatives and the directional derivative, and here we're going to culminate in a very important, very useful section of this entire course, and that is the concept of the gradient, okay? So when you're studying this stuff for the first time, it's difficult sometimes to keep straight in your head the differences between some of the things we're talking about. So I'm going to do a little bit of recap here, and then we're going to go into the gradient, which at first glance might seem like we've already covered it, but in fact it's a little bit different than everything we've done so far, okay? So the first thing you need to remember is we talked about the concept of a partial derivative of a multivariable function, okay? And that just means you take a partial along x or a partial along y, or if it's a 3D function, a partial along z, and that just means you're finding the derivative in those directions. How the function changes as you move along x, how the function changes as you move along y, how the function changes with respect to z. That's what the partial derivative is. Then we introduce the concept of the directional derivative, which is sort of a generalization of that whole thing. And what that is you want to take the partial derivative of a function in any arbitrary direction you want. Maybe I want to know how fast the function changes in that direction. Maybe I want to find out how fast it changes if I look that direction. And we derive the formulas and we use the formulas for the directional derivative. And really all we were doing was taking the partial derivatives and mixing them according to the vector direction we cared about and weighting them appropriately according to the unit vector that we cared about, which we called a. So the directional derivative was noted d sub a. Okay, that's what we've learned so far. What we're going to do in this section is we're going to introduce our first vector operator, okay, which is going to be a vector operator. I'll show you what it looks like. It's going to operate on a function, and it's going to return a vector, okay? So we have some 3D functions sitting out before us. It's a function of x and y, and you could draw a representation on a coordinate system, okay? You plug in, or you apply, I should say, you apply the vector operator called the gradient to it, and basically what it's going to return in the end of the day, it's going to return a vector. The direction that that vector points, is going to always be the direction that the function is increasing most rapidly. Okay, that's very important, okay? So, you know, like we said before, you can take the partial along x and the partial along y. And you could take the partial in the arbitrary a direction and figure out how fast the function's changing in any of those directions, okay? But when you apply the gradient operator, think about what the term gradient means. I mean, it almost sort of sounds like you're trying to figure out the slope of something, right? And that's exactly what it is. You're going to operate on the function, and whatever vector you get back from that operation is always going to point in the exact direction of maximum slope. Okay, so you have this sort of 3D function sitting out in front of you. At any given point on the surface, depending on which way you look, the function may be sloping up or down. It may be increasing or decreasing. Okay, and what the vector operator gradient does is it always points, the vector that it returns always points in the direction of maximum increasingness of the function. And the length of the vector returned by the gradient operator is actually the value of the rate of change at that point. So you get the direction and you get the magnitude of the rate of change. Okay, so we're going to go ahead and work some things here. The gradient operator is used everywhere in engineering and advanced math, so it is a very important operator. It's definitely one of the most important things in the class. Okay, so let's go ahead and just sort of write down what I talked about a little bit. Just a little bit of review. You remember partial of x with respect to x, this is just what we call the partial derivative. Okay, and what we said this was the rate of change, triangle means change, rate of change of f of x, y, which let's say it's a function of two variables in the x direction. So here I'm looking as I go back and forth along x, what is the rate of change of this function only looking in the x direction? Likewise, we define the partial with respect to y, which we denoted as f sub y, and that was the rate of change of the function that we're talking about, the function of two variables, but now we're talking about in the y direction. The y direction, okay? And then, that was several sections ago, and then we defined the directional derivative, okay, which was along some vector a, the directional derivative of f in the direction of a, which is an arbitrary direction. The reason I've got a caret on top of the a is because, remember, we always had to use a we always had to use a unit vector to describe the direction that we cared about. And we talked about why we needed to do that in the last section, so that's why it's got a little caret there. But it's basically a direction vector. It tells me what direction do I care to evaluate and find the slope of this function. And what that is a mixture of the partial derivatives that we already know how to calculate. That's all it is. You have the partial along x, the partial along y. We know how to do that, and we're mixing them. We're weighting them, so to speak, according to the coefficients of this vector direction we care about. So if the vector lies purely along x, then a1 will be 1 and a2 will be 0, and so you'll have no contribution of this partial. Likewise, if a lies purely along y, this will be 1, and this will drop out because there will be no component along x, so this a1 will be 0. And anything in between is basically going to be a mixture of the partial derivatives, okay? And we already talked about this, but the vector a was a1 in the I direction plus a2 in the j direction. That was just the direction vector that we cared about. So it's the rate of change of f in any arbitrary direction a that we care about, okay? So now we're going to define the vector operator called the gradient. I'm going to write it down. I'm going to write a few words down below it, and we're going to talk quite a bit about it, and we're going to work some problems. So the vector operator which is called the gradient. I'm going to underline it because it's a new term. It's called the gradient operator. Okay, you write it with an upside down triangle. And personally, you know, this is the case when you start to get into Calculus 3 and you open up an advanced calculus book and you start seeing these crazy symbols, and it throws people off immediately, and you might get scared and frightened and turned off by the whole thing. But this triangle is just, they just had to write something to denote this gradient. I mean, you can also actually call it the grad. Okay, the grad. A lot of times people actually use that term grad to talk about that. Okay, so you have an upside down triangle, which is also called the gradient operator, and you can also use the term grad. Okay, sometimes you see that in books. Most books you'll see the upside down triangle. Okay, and what this operator is equal to the partial derivative with respect to x in the I direction plus the partial derivative with respect to y in the j direction plus the partial derivative with respect to z in the k direction. Okay, so burn that in your head because this is exactly what the gradient operator is. I don't expect you to understand what it means or how you would use it or why it works or anything else, but that's what it is. The triangle symbol, anytime you see this in your book, anytime you see this in an equation, a formula, for instance, you see these all over the place in Maxwell's field equations of electromagnetics. They're all over the place. And so you have to know what this means. The upside down triangle just means it's got an x component, a y component, and a z component. And notice that there's really no function in here. There's just an operator going on. You have you're taking the derivative of something with respect to x and you're putting it in front of the I hat, taking the derivative of something with respect to y and you're putting it in front of j hat, and you're taking the derivative of something with respect to z and you're putting it in front of k hat. So what this is doing is you're taking the derivatives in all three directions and you're putting the answers in front of the unit vectors, okay? So what you're getting back here, when you apply this upside down triangle to a function, you're getting a vector back. That's exactly what you're getting, okay? So for instance, and I'm not going to solve a problem here, but just to sort of show you. Okay, so let's recap here. We have this vector operator, which we have here, and we've defined it as the partial of, there's nothing written here, so it's the partial of whatever function we're applying it to with respect to x in the I direction, plus the partial with respect to y in the j direction, plus the partial with respect to z in the k direction, okay? Now what happens when you apply that to a function? And I haven't even really given you the big picture of what we're doing this for, but I'm just trying to tell you it's an operator. So what it does is you write it usually with the triangle applied directly to a function f. In this case, let's say it's a function of three variables. So what you're doing is, because the triangle by itself is just the partial with respect to x and y and z in those different directions, then when you write it down in all of its glory when you're actually operating on a function, it's the partial of f with respect to x in the I direction, plus the partial of f with respect to y in the j direction, plus the partial of f with respect to z in the k direction. So when you operate with the gradient onto a function, you're actually going to end up taking derivatives of that function in all three directions, and you're putting you're putting whatever you get as a result in front of the various components. So what you're going to get effectively is you're going to get a vector out, okay? And these are partial derivatives, and so you're going to get functions of x and y everywhere. But effectively what you're getting is a vector, okay? And you're going to get a vector function back. And what we're saying and what we said sort of in the introduction is that what this vector is going to do is it's always going to point, whatever point in space you're interested in, it's always going to point in the direction that the function f is increasing the most. Okay? So I want to write that down in words, and you're not going to really probably totally understand it until we get to the problems, but that's basically what's going to happen. Okay, so the way you write that is you say, when the gradient which is denoted by the upside down triangle, operates on a function when it operates on a function, and that function we're going to call f, like we always do, the result is a vector. Okay, the result is a vector because it has three components, x, y, and z, okay? And that vector is really going to be denoted as gradient of f, okay? Whose direction at a given point points in the direction that f increases, that's what INC means, increases most rapidly. Okay, one more sentence. The magnitude of this vector is the rate of change of f at that point. Okay. What I've tried to write here, hopefully, is nothing more than I've already told you in the introduction to the course, okay? So big picture. You're defining a vector operator that looks like an upside-down triangle. It's defined as the partial derivatives of whatever function you're applying it to in all three directions, and you take the results and you stick them in front of these vector unit vectors here. So when you actually apply it to a function, you're going to be taking the partial derivatives of f in the three directions and you're putting them in front of the unit vectors, okay? So what this is saying is that when you take and you do this operation, you're going to get back when the gradient f operates on a function f, the result is a vector. The reason it's a vector is because the definition of it has an I component, a j component, and a k component. So when you take the partial with respect to x, there's going to be some little function here. I mean, when you take you remember we're taking partial derivatives all day long a few sections ago. When you take the partial of f with respect to x, there's going to be x's and y's and z's right here in this little nugget, okay? When you take the partial with respect to y, there's going to be x's and y's and z's right in here. When you take this partial, there's going to be x's and y's and z's in there. So it returns a vector, but really it's a little more complicated than that. What it's returning is it's returning a vector function such that you can, you know, in the same way back with the regular derivatives, okay? When you take the derivative of f, just a regular plain Jane calculus derivative, you get another function of x, right? You get another function back, so that whatever point you want to plug in for x, you'll get the slope of the curve, okay? What this is doing is you're getting a vector back, okay, whose direction at a given point always points in the direction that the function f is increasing most rapidly, okay? So what this says is that you're going to get back a vector, quote unquote, but every component of the vector is going to be a function of x, y, and z. So what it says is, in the end of the day, if you want to plug in x and y and z into this gradient that you get back, then you will get an actual vector back that at that specific point will always point in the direction that f is increasing most. In exactly the same way that when you take a linear regular derivative, you get derivative of x squared, you can plug in x is equal to 10, and you will find the value of the slope of the line tangent to that curve, the original x squared curve, at that point. So when you take the gradient, you're going to get a pretty complicated looking thing back. You're going to get a bunch of a function here, and a function here, and a function here that's going to be multivariable in each place. But all it's doing is it's telling you that at every point in three-dimensional space, at every x, y, and z, I can plug it into whatever gradient I get, and that is going to reduce down to a vector that I get back. It's going to actually be a vector, a number, and a number, once I plug in the point that I care about, and the direction that this vector points is going to be the direction that the original function increases most rapidly, and the magnitude of that vector that I get back is going to always be the rate of change of f at that point. So the gradient is telling me how fast the function is changing in the direction that it changes most rapidly. It increases most rapidly. So we were doing the directional derivative earlier. That's when I was picking the direction that I wanted to find the slope here. That was when I cared about finding about, you know, how fast does this thing change in this direction? What's the magnitude of the rate of change in this direction? The gradient is a little bit different. It's when I'm given a function, I don't know squat about it, I just know I have a function. I want to find out at this point in space right here, what is the direction this function is changing most rapidly? Okay, and so I can apply the gradient to it, plug in the x, y, z coordinates of this particular point, and I will get a vector back. And that vector will always point in the direction that the function is increasing most, and the magnitude of that vector will be the derivative effectively in that direction. Okay, so it will be effectively the directional derivative that we learned about most. Okay, so because of this, because of the definition and how they're sort of related, I'm actually going to write it like this. Because of this, okay, the derivative in the a direction of f at the point x sub 0, y sub 0, let's say it's a function of two variables, okay, is going to be equal to the gradient of f evaluated at this point, which is going to return a vector, by the way, dotted with a, okay? Dotted with a. Now, why does that work? Just think about what you're doing here, okay? What we're saying is if you take the gradient, what this is going to return is it's going to return a vector, basically, that always is going to point in the direction that f increases most rapidly, okay? We're going to dot that with whatever direction we care about. Basically, it's another formula, it's another relation showing you how to calculate the directional derivative. That's all it is, okay? And the reason it works is because what does the gradient of f look like? It's the partial of f with respect to x in the I direction, plus the partial of f with respect to y in the j direction. If it's a two-dimensional function, all you have is the I and j components, okay? Now, that's what we said is inside of here, and let's just see what happens if I dot it with a here. A hat is a sub 1 in the I direction, plus a sub 2 in the j direction, okay? That's what you have to do. Now, this is a dot product, just like you've always learned, right? So how do you do a dot product? I mean, if you have 2i plus j, and you're dotting that with 3i plus j, then what you do is you just multiply the components together. So it's 2 times 3 plus 1 times 1, like that. So it's 6 plus 1 is 7. Okay, that's how you take a dot product in general. This is no different, okay? This is no different than what you've already learned and what you've already know how to do. So when you actually do that, okay, so if you do this, this component times a1 is just going to be partial of f with respect to x multiplied by a sub 1 plus partial of f with respect to y multiplied by a sub 2. This is exactly the definition I gave you before of the directional derivative, okay? The directional derivative in the direction of a. We said we take the partial with respect to x, multiply it by the component in the x direction of the vector we care about. Same thing with the y component. This is exactly what you saw in the last section, okay? So what I'm showing you is I'm reverse engineering that this directional derivative is equal to the gradient dotted with the direction that I care about. So it's almost like I'm taking the direction that the function is increasing the most and dotting it in the direction I care about, and that is going to also be the directional derivative. The only reason I even bring this up is it's sort of an application of the gradient, and you'll see it in your textbooks, and they might ask you on the test to calculate the directional derivative using the gradient operator. So all you'd have to do is calculate the gradient and then dot it with the direction you care about that's given to you in the test, and you get the answer. Okay, so let's go ahead and work some problems and see how we can use the gradient and make some sense of what it's trying to say. So here is a function of two variables, x and y, okay, and this function is 3x minus 5y. Okay, so that's a function of two variables. So in your coordinate system, the xy plane down here is the variables that you plug in, and you get your f of x comma y out, which is your third coordinate going up and down. So if you can sort of visualize, this function of x and y being this kind of this three-dimensional thing hovering over the xy plane, that would be this function as a function of the two coordinates in the xy plane. Okay. Now, what do we want to do? What we want to end up doing in all of these problems is we want to find the gradient of the function f. Okay, that's what we want to do, and that's exactly how you write it. So you have the gradient operator, which we've just talked about what that is, and it's operating on this function f, and it's going to return something, and we'll talk about what it returns. Now, remember, or recall, I should say, that the gradient itself, the gradient as an operator, is written as the partial with respect to x in the I direction, plus the partial with respect to y in the j direction, plus the partial with respect to z in the k direction. So the partials are all going in their respective directions, and the component of the unit vectors are also there. So the x derivative in the x direction, the y derivative in the y direction, the z derivative in the z direction. That's the operator. Now when you actually operate on the partial, when you operate on the function f, then what you're doing is you're applying this whole vector operator, okay, to this function. Okay, so what we have to do in order to calculate the gradient, okay, is really actually pretty easy. So what you do is you're literally going to write it as upside down triangle with an f there. So the gradient operates on the function f, and what it's going to give you is when you actually, if you were to take this and sort of apply it to this function here, what you have is the partial of f with respect to x in the I direction, plus the partial of f with respect to y in the j direction, plus the partial of f with respect to z in the k direction. So you see there's no magic here. You're just taking this guy and you're applying it to f. So you're taking the partial of f, the partial of f, the partial of f in every case, and so that's all we have to do. All we have to do is now calculate these partial derivatives, and we'll have our gradient. Okay? So let's go ahead and do that. Gradient of f is equal to, what is the partial derivative of f with respect to x? We're only taking the derivative with respect to x, so y is a constant. So what this is going to look like is taking the derivative of the 3x is going to give me the 3. The derivative of this with respect to x is 0 because y is a constant there, because I'm only taking the derivative with respect to x. So what I'm going to have is 3i. Okay, that's all that goes in front of the I. Okay, now taking the partial derivative of this guy with respect to y, similar sort of thing. Plus, what is the partial of this with respect to y? Well, x is constant in that case, so that's going to be a 0. Partial of the derivative of this is 0 if x is constant. And over here, you're just going to have your negative 5. So you make this a negative 5 in the j direction. Okay, and what about this? Can you take the partial derivative of this function with respect to z? No, you can't. You really can't do it because there really is no z dependence. It's not even a function of z. So in general, the vector operator is three-dimensional, the gradient, but if there is no dependency on z, if this function is not a function of z at all, then it's just 0. There's nothing that contributes. So this is the answer. This is the gradient of this function f. Okay? Now notice in this particular case, remember what the gradient is telling you. The gradient is telling you that at a certain point that you're interested in looking at, it tells you the direction and the magnitude in the direction of the slope of the function in the maximum increasing direction. So let me say that one more time. When you calculate the gradient, which is what we've done here, we got a vector back, 3i minus 5j. What it's saying is that it's pointing all the time in the direction that the function f increases most. Okay? And the direction it points is the direction that it increases most, and the magnitude of the vector is the magnitude of the rate of change in that direction. Okay? Now in this particular case, because it's a very simple function, okay, all over the xy plane, if I pick any point in the xy plane, there's no dependency in this guy here. It's a constant. There's a 3i minus 5j. There's no x's and there's no y's in here. So the gradient is actually a constant in this case. That means that it doesn't change as you move around the xy plane. The gradient, or I should say the direction that f increases most is always pointing in exactly the same direction in this particular example because the function is so simple. Okay. Now most of the time you're going to have more complicated expressions in front of I and j, and so the gradient, in other words the direction of the maximum slope, is going to change as you move around the xy plane. Because you can kind of imagine in the most general sense, you might have a function, you know, like this is your xyz, you may have some crazy function with hills and valleys, and you know, you'll have to use your imagination here because this is a three-dimensional surface, right? So this could have hills and valleys, but it's a three-dimensional sort of construct. So depending on where you're looking in the xy plane, the gradient, which is the direction of the slope increasing the most, here is going to be different than it is going to be right here, which is going to be different than it is here, okay? But in this particular example, no matter where I look in the xy plane, okay, the direction that f increases most is fixed. It's fixed by this direction here, whatever 3i minus 5j is, the direction of that vector. The magnitude of this vector that we just calculated here is the magnitude of the rate of change in that direction, okay? So in general, you're going to see more complicated things come out of the gradient function, but this is a pretty simple example to start. And honestly, that's why I think it's a good example to start with, is it gets the point across a little bit easier. So let's go and do something a little bit more complicated. Let's say you have a function g of x and y, function of two variables yet again, and it's equal to e to the negative 2x times the natural log of y minus 4. So this is a complicated looking expression. I certainly would have no idea what it actually looks like. E to the negative 2x times the natural log of y minus 4. And what I want to do is calculate the gradient. So I want to calculate the gradient of g. And if you look back up at your definition of what the gradient operator is, it's just the partials in the different directions with the unit vectors. Okay? If you operate on g, what you're going to have here is partial of g with respect to x in the I direction, plus the partial of g with respect to y in the j direction, plus the partial of g with respect to z in the k direction. Now in general, I write this down in all of its glory, but you can see here that the function is only a function of two variables, so there's not going to be any k direction going on here because there is no dependency in z. This function is not even a function of z. So this part's going to drop out, but I'm writing it for completeness. Okay? So first thing you have to do is just go ahead and take these partial derivatives. You see, it's calculating the gradient isn't a big deal. You just have to know how to write it down. Now you can do it using your partial derivatives we've talked about before. So the gradient of g, okay, is going to be taking the derivative of this function with respect to x. Now if we do that, this is the only thing that has an x in it. This guy has a y in it, and then basically this is a constant because I'm only taking the derivative with respect to x. So this entire thing is a constant. So I'm going to write the constant out in front just because I like to do that. Okay, so this is a constant because I'm taking with respect to x. Now I have to take the derivative of this actual function of x here. The derivative of a power of e is just the same power of e times the derivative of the exponent, which is negative 2. The derivative of negative 2x is negative 2. So remember, this was a constant, so he came out because I'm only taking with respect to x. Taking the derivative of this is what gives me that. Okay, now this, don't forget, is in the I direction. You always have to keep your directions. That's just as important as calculating the derivative. If you don't have this I hat, then the thing is not going to give you a vector back, and it's going to be meaningless. Okay, so we've got this plus, what is the partial derivative of g with respect to y? Well, if I'm taking the derivative with respect to y, this thing is constant, and I would only take the derivative of this. So this being a constant is going to be e to the negative 2x times. If this is when I'm taking the derivative with respect to y, the derivative of a natural logarithm is 1 over the argument, in this case y minus 4. But I have to multiply by the derivative of the inside, so I'm taking the derivative of this guy, which is 1. Derivative of y is 1, derivative of 4 is 0. Okay, so this is going to be the second term, and he's going to be in the j direction. And just for completeness, this is the first term right here in the I direction. This is the second term in the j direction. Again, this is what you're taking the derivative of. This thing is just a constant. He comes along for the ride. Okay, so this is the answer. All you have to do is simplify it a little bit, and let's go ahead and do that right now. So the gradient of g, okay, I have a negative 2 right here, so I'm just going to write that out front. Negative 2e to the negative 2x times the natural log of y minus 4, and you can put some big brackets out there just to kind of help you keep it straight. And this is supposed to be the I direction, actually. So this is the I direction, or the x direction, okay? And then I've got this guy on top and this on bottom, so I'm just going to sort of rewrite it as e to the negative 2x over the denominator y minus 4. It's sort of a simple little rewriting here, just to kind of make everything pretty. And then this is in the j direction. Okay, and obviously there is no partial of g with respect to z, because there's no z anywhere in here, and the function is not even a function of z. So this is the full glory of things, but you don't really have to write anything down because that derivative is 0. So this is the gradient of g, negative 2 e to the negative 2x times natural log of y minus 4 in the I direction, plus e to the minus 2x over y minus 4 in the j direction. Now what does this mean? What this means is that you're given some function of two variables. So again, you have to try to do some visualization. If this is the xyz plane, this function is some sort of function of x and y up here. It has some crazy shape, all right? And it hovers over the xy plane. I'm plugging in numbers into the xy plane, x comma y, and I'm getting out values that correspond to how high this thing is above the xy plane, okay? So what am I doing when I take the gradient is, if I pick any point in the xy plane down here that the function's defined upon, and I take that point and I plug it into this equation, because this equation has x's and this equation has y's. If I take an xy and I put it in here, I will get a number. This will reduce to a number in front of the I, and this will reduce to a number in front of the j. And so that would be a vector, a number I plus a number j. And at that specific point that I'm calculating the gradient, okay, I will get a vector. And that vector will point in the direction, by definition, of maximum increasing slope at that point. And the magnitude of this vector that you get at that point is going to be the rate of change of the function, the actual derivative of the function in that direction. So you see what you're doing here, much in the same way, and I briefly talked about this before, much in the same way of a regular derivative, y is equal to, or f of x is equal to 2x, or f of x is equal to x squared. And so what you're doing there is you got another function. That function is defined along all of x, and you plug in values of x, and you're getting the value of the slope at that point, okay? Here, you're calculating a gradient, and when you do it in the general form, you get a function of xy in front of I and a function of xy in front of j, and that's a general function that you can then plug points into, and what you're getting are vectors at every point in the xy plane. And that vector that you get as a result points in the maximum increasing direction of slope, and the magnitude of it is the value of the derivative in that direction. So the gradient is really a way to calculate the maximum slope along a mountain, or the maximum slope of a function of two variables or a function of three variables when you don't know ahead of time what that direction is. So it's very important when you look at basically any engineering or physics textbook, you know, for electromagnetism, quantum mechanics, anything, they're all going to have these upside down triangles, and that's nothing more than the vector, the gradient operator, basically. Okay, so you'll see different, we'll talk a little bit about different operations that you can use along with this triangle, but if you see a triangle right next to a function, right there, that is called a gradient. That's what we're doing here. So let's go ahead and work another one and just get a little bit more practice. What if you have a function of three variables? You'll see very quickly that the math is no more difficult. If it were 2x squared minus y squared minus 4z squared, okay? So in this case, it's not just a function of x and y plugging in and getting some value of z. This is really and truly a three-dimensional function. At every point in space, x, y, and z, I arrive at a value back. It's really hard to draw those kinds of things, but that would be sort of like if I had measured the temperature in this room at every point in space, in three-dimensional space, and I correlated that to a function, then I can predict the temperature at any point in the room by plugging it into a function of 3 variables like that. But if you're wanting to find the gradient, effectively telling you at every single point what direction the temperature, let's say, is changing most rapidly, then you would do it just the same way as you always do it. The gradient of f is the partial of f with respect to x in the I direction, plus the partial of f with respect to y in the j direction, plus the partial of f with respect to z in the k direction. Okay, so here I'm writing it all down as I've applied it to the function f, and so you just take your partial derivatives accordingly. Okay, so let's go ahead and do that right now. So the gradient of f is going to be, what is the partial derivative of this function with respect to x? Well, this obviously has an x, this is y, and this has a z in there, so these are going to be constants. So the derivative of these guys are going to be 0, but this first thing is going to give me 4x in the I direction. 4x in the I direction. The derivative of these things are 0 because they're constants, because I'm taking only with respect to x. Plus, partial of this thing with respect to y. Same kind of thing. This is going to be a constant, this is going to be a constant, because everything other than y is constant when I'm taking the partial derivative like this. So I'm going to have 0, I'm going to have, just going to erase this, negative 2y in the j direction, because the derivative of negative y squared is negative 2y, and the derivative of these things are 0 because they're constants now. Okay, and then what I'm going to have over here is the derivative of this thing only with respect to z. That means this is a constant, now this is a constant. So all I have to do is take the derivative of the negative 4z squared, which is giving me negative 8z in the k direction, negative 8z. Okay, so you can see here 2 times 4 gives me the 8, and you have the z in the k direction. So again, that is the answer. You're just taking the derivatives in the different directions and you're sticking them in front of the unit vectors. And again, what you have arrived at here is a new function, okay? And this new function has x's and y's and z's in it, okay? So if I take this new function and I pick a point in space, let's say right here, you know, and I plug x, y, and z value in here, then it will tell me that at this specific point in space, right here, okay, when I plug in x, y, and z right here, whatever value I get back for the vector, okay, that I actually calculate out of this thing, ijk component, it's going to tell me the direction that this thing is changing most, increasing the most, and the magnitude of whatever I calculate at that specific point is going to be the rate of change of the function, the slope of the function. So it gives you two things, the direction and the magnitude of the rate of change, which is what you're looking for. So every time you calculate a gradient, you're going to get a function that defines at any given point in space, okay, what the direction of maximum increasing this is, so to speak, for that function. Okay, now we're going to build upon that topic, and in this case we're going to calculate the gradient just like we always have, but we're going to take it one step further and hopefully tie all of this together. X times the natural log of x plus y. Okay, that is what we're going to do. We could calculate the gradient of this thing just like we were doing, but what we want to do is we want to evaluate the gradient at the point negative 2, 3. So this problem, we're going to calculate the gradient, but then after we actually calculate the gradient, we're going to evaluate the gradient at a certain point and see what that tells us. Okay, so again, let's write down what the gradient is. The gradient of g is equal to the partial of g with respect to x in the I direction, plus the partial of g with respect to y in the j direction, plus the partial of g with respect to z in the k direction. That's what the gradient is. Let's go ahead and calculate it. Okay, so the gradient is going to be, what is the derivative of this function only as a function of x? So that means I'm only taking it with respect to x, so y is now constant, okay? So you can see I have a function multiplied by another function, so I'm going to have to use the multiplication rule of your derivatives from your calculus 1. So the first little function times the derivative of the second plus the second times the derivative of the first. So let's go ahead and do that. So what I'm going to have here is the first function, which is x, times the derivative of the second, but only with respect to x. That's what I'm doing. The derivative of the second is going to be 1 over x plus y, because derivative of a logarithm, natural log is 1 over the argument, But then I have to multiply by the derivative of what's inside, but I'm only taking the derivative with respect to x. So I'm only going to have a 1 in here because the derivative of x is 1. The derivative of this thing is just a constant, so he's 0. So he stays away. So I have the first times the derivative of the second, okay, plus the second function, which is natural log of x plus y, times the derivative of the first, and which is this, and I'm taking it with respect to x, so that's just going to be a 1. This, my friends, is all in the I direction. So I've just taken the derivative of this with respect to x, and I've stuck it right in front of the I unit vector, which is the x unit vector, and I'm going to go ahead and help you out visualizing this a little bit. All of this stuff is in the I direction. Okay, try to change colors a little bit for you. Okay, so we have x, or x plus y. Yep, that's right. Okay, and then next let's go on and calculate the next thing here. So I have a plus. I have a plus. And now I'm going to evaluate the derivative of this with respect to y. Okay, with the derivative with respect to y. So again, it's first times the derivative of the second plus the second times the derivative of the first. So the first is x times the derivative of the second. There's 1 over x plus y for the same reason, because it's a natural log, but I have to multiply by the derivative of the inside because it's a nested function like that. Now in this case, I'm taking the derivative only with respect to y, so x is constant, so the derivative of this guy is 0, the derivative of this guy is 1. So far it looks exactly the same. First times the derivative of the second plus the second times the derivative of the first. Now this is where it gets interesting. This is an x. I'm taking the derivative only with respect to y, so this is a constant. That means the derivative is 0. Okay? And this is all in the j direction. Okay? Now what this tells me is this entire term falls out to 0. Okay? That entire term falls out to 0. So how do we go ahead and make any progress here? The gradient of g is then going to be equal to x over x plus y, just doing this right here, plus the natural log of x plus y, all in the I direction, plus, let me go ahead and change colors here just to make it a little bit clearer. This is all in the I direction, okay, plus what I have here, x over x plus y, and that's all I have here because this goes to 0, and this is all in the j direction. So we've arrived at the same place we've already arrived at all of these problems. We've calculated the gradient x over x plus y plus natural log of x plus y in the I direction, plus x over x plus y in the j direction. That is the general form of the gradient. That means that you can plug values in for x and y, which are going to be here on the plane, you know, that the function's defined upon, and I'm going to plug these values in, and I'm going to get vectors at every single point, and that vector is going to point in the direction that this function g is increasing most, and the magnitude of this thing is going to be the actual magnitude of the rate of change. How much is it changing? So what we're going to do next is, this is the general form for the gradient, valid at every point in the xy plane, but now we want to evaluate it only at the point negative 2 comma 3. Okay, negative 2 comma 3. So we want to actually see what is the gradient at a specific point, okay? So the way you would write that is gradient of g evaluated at negative 2 comma 3 is equal to. So I have to plug in for x is going to be negative 2 over negative 2 plus 3 plus the natural log of negative 2 plus 3, and this is going to be in the I direction, okay? And then over here, what I'm going to have is going to be plus negative 2 plus 3, and that's going to be in the j direction. Okay, so let's go ahead and simplify what we have here. So the gradient of negative 2 comma 3, or evaluated at negative 2 comma 3, it's going to be negative 2 over 1, because this is going to be negative 1 in the denominator. So what I'm going to have effectively is negative 2 plus natural log of 1, right? And that's going to be in the I direction. Okay? Going to be in the I direction. And then this is going to be plus negative 2 over 1, so I'm going to have negative 2, and that's going to be in the j direction. Okay? Now let's evaluate this further. What is the natural log of 1? I think you can probably convince yourself that this thing is actually equal to 0, because what it means is e, because it's base e to the power of what gives me 1. The only thing the way that's going to happen is if e is raised to the power of 0, that would give you 1. That's how you evaluate your logarithms. So this entire thing is 0. So what you've really calculated in the end, go ahead and use the same color here, is the gradient of g evaluated at negative 2 comma 3 is equal to negative 2 in the I direction, okay, minus 2 in the j direction, because this is 0. That is the gradient evaluated at negative 2 comma 3. So you see, we calculated the gradient, we got that actually right here, and then we evaluated that at a very specific point in the xy plane. And we got a vector back, a real vector with numbers in front of the, just like the vectors that we talked about in section 1 or section 2 of the class. This is nothing fancy. What this vector means is the direction this vector points in the xy plane is the direction that g is increasing most rapidly at this point, okay? So that's what it's doing. It's pointing in the direction that g is increasing, okay? And the magnitude of this thing is the magnitude of the rate of change, or how fast g is increasing. So it tells you two things: the direction g is increasing most there, and it's telling you the magnitude of the rate of change, okay? So what are we going to do next? Let's go ahead and do one more. It's really not going to be any difficult, or otherwise harder. It's just going to be a little bit more of the same. F of x, y, z. The only thing different is now this is a function of 3 variables. We're going to do the same kind of thing. We're going to say z times e to the negative x, this is the function, times tangent of y. Okay? And I want to evaluate this at the point 0, comma, pi, comma, negative 2. Okay, so that's my function, z e to the negative x times tangent of y, evaluated at that point. So I want to calculate the gradient, I'm going to get that, and then I'm going to evaluate it at this point, and the resulting vector is going to tell me what direction this function is actually changing the most, and the magnitude of that vector that I get back is going to be the actual value. How fast is the thing changing in that direction, okay? So the gradient of f is equal to the partial of f with respect to x in the I direction, plus the partial of f with respect to x in the j direction, plus the partial of f with respect to z. Sorry, I made a mistake here. This is y, and this is the k direction. Okay, so I just have to take my partials and go about my merry way. So let's do that right now. Gradient of f is equal to, what is the partial derivative of this with respect to x? Since it's taking it with respect to x, that means the z and the y's are constant, and the only thing I'm actually taking the derivative of is this thing. So because these are constants, and then I'm actually taking the derivative of this, I'm just going to pull these constants right on out, just like I do with any derivative. So they're going to come first. Now let's take the derivative of this. It's going to be e to the negative x times the derivative of the exponent, which is negative 1. Okay, the derivative of an exponential is the exponential itself times the derivative of whatever's up in the exponential there. Okay, so this whole thing that I just wrote down here is in the I direction. Okay, it's going to be in the I direction. Okay, now let's move on and calculate the next component, plus. Okay, what is the derivative of this function with respect to y? Okay. If I'm taking with respect to y, that means these things right here are all constant. So I'm going to write them just out in front, along for the ride, because they're constants. Now I'm going to take the derivative of this thing with respect to y. Derivative of tangent is secant squared y. Okay? And this whole thing is going to be in the j direction. Okay? That whole thing is going to be in the j direction. Okay? And then the next thing I'm going to do is I'm going to take the partial derivative with respect to z. Okay, now that would mean I'm taking the partial with respect to this. This is a constant, this is a constant. So the constants are going to be written, e to the negative x, they're going to come along for the ride. Now let's take the derivative of the actual z thing, but the derivative of z is 1, so it's just going to be multiplied by 1, so I'm really done. Okay, and that's going to be in the k direction. Okay, so the gradient that I've actually calculated is z times tangent y, e to the negative x, to the negative 1, or multiplied by negative 1, and that's in the I direction, then z e to the negative x secant squared y in the j direction, and then I have e to the negative x tangent y in the k direction, okay? So this is it. The only thing that I would do if I'm going to simplify anything is I'm going to take this -1 and stick it in front here, but that's really trivial. So what I'm going to do next is just actually go ahead and plug in the value of the point that I care about and evaluate this gradient at a very specific point to see which direction this function is changing and increasing most rapidly at that point, okay? So let's go ahead and do that next, okay? So the gradient of f evaluated at 0, pi, -2 is going to equal, okay, z is going to be equal to -2, so I'm going to have -2 times the tangent of y, which is the tangent of pi, times e to the negative x, so it's going to be e to the negative x, but x is 0, so it's going to be e to the 0, times -1. The -1 comes along for the ride, and this stuff is all going to be in the I direction. Okay? Plus, let's evaluate this. Z is equal to -2, so I'm going to have -2. E to the negative x is e, x is 0, so it's going to be e to the 0. Secant squared y, this is y, so it's going to be secant squared of pi, and that's going to be in the j direction. Okay, and then finally, I'm going to evaluate this guy at those points. E to the negative x is going to be e to the 0, because x is 0. Tangent of y is tangent of pi. And all of this is going to be in the k direction. Okay, got my x component, y component, z component. Let's see how it all simplifies here. Okay, so what I'm going to have, the negative times the negative is going to give me a positive, right? So right away I'm going to have a +2. The tangent of pi, I think you could probably convince yourself is 0, because tangent is sine over cosine. So the sine of pi over the cosine pi, on the top, sine of pi is 0, so it's going to chop the whole fraction down to 0. Or you could just use your calculator, however you figure this out. The tangent of pi is actually 0. So I'm going to have 2 times 0, e to the 0 is 1, and I'm going to have -1 here. Really doesn't much matter. This whole thing is going to go to 0, right? So that's going to be in the I direction. Okay, plus, let's do this part here, okay? I'm going to have -2, e to the 0 is 1, so I'm going to have -2, e to the 0 is 1, and now I'm going to rewrite the secant. Remember, if you write your trig functions as sine, cosine, tangent, cotangent, secant, cosecant, the secant is the inverse of the cosine. So I'm just going to write it in terms of cosine because I'm more comfortable evaluating cosines than secants. Okay, so I'm going to write it like that. E to the 0 is 1, that's why it drops out, so this is in the j direction. Well, let's go ahead and evaluate the last thing, and then we'll be just about done here. Plus, inside of here, I'm going to have the same kind of thing. E to the 0 is 1, but tangent of pi is 0. And that's all in the k direction. Okay, so what you can see right away is that this entire component goes out to 0. This entire component goes out to 0. So effectively, there is no I component or k component in the actual answer, and so they all drop away. So what you can do is you can rewrite the whole thing as the gradient of the function f at the point 0, pi, -2 is going to then equal -2 over. What is cosine of pi? Cosine of pi, I think you can convince yourself, is -1. So you're going to have -1 squared, okay? And that's going to be in the j direction. And so the gradient of f from at 0, pi, -2 is going to equal -2 over 1 is -2j. -2j. So what you've gotten here is a final answer, and what it tells you is that you've calculated the gradient of the original function, which is way, way up here. It's a function of 3 variables, okay? But when you calculate the gradient and evaluate it at this very specific point here, x, y, and z, what you find is that the function increases most rapidly in this direction, which is purely the j direction. That's the direction there. So basically it increases at that point most rapidly in the y direction because j corresponds to y. And the magnitude here, the magnitude of this vector is 2. That's the magnitude of the rate of change, or the magnitude of the increase at this point, or at the point that we're talking about here, okay? So, you know, just as an aside, I mean, we've talked about this before, but your XYZ representation of things, we have, let's say you have a function that looks something like this, and it's kind of hovering over the xy plane here, okay? What you're doing when you calculate the gradient at a certain point, let's say we're evaluating the gradient at this point here, what you're doing is you're basically finding, kind of looking up here along the function right here, what direction does the rate of change increase most? Is it this way, or is it this way, or is it this way, or what direction is it? Well, when you find the gradient and you plug in the point that you care about, you basically are finding the direction that the function increases most rapidly, and the value of the actual magnitude of the vector that you're talking about corresponds to the actual magnitude, or how steep the thing is at that point, okay? So this section we have conquered and tackled the subject of the gradient, which is a vector operator that operates on a function. Regular old plain Jane functions. They're functions of 2 and 3 variables, but they're regular functions, okay? And the vector operator called del, by the way, I don't even think I told you that. The upside down triangle is actually referred to as del, D-E-L, okay? That's the del operator. When you operate on a function, you get back a vector. In the most general case, you get back a general vector like this. So this is a function of x, y, and z at every I, j, and k. Okay, this is a general function that tells you at any point x, y, and z, I can get the slope of the direction that the function is increasing most rapidly, and also its magnitude, and that's why it's useful. It lets me look at an arbitrary function and figure out at every given point what direction is this function increasing most rapidly. That's why it's useful. That's why it's called a gradient. Okay, and with practice, I think you'll get the hang of it. The biggest challenge of it is that you're really going to be taking a lot of partial derivatives and holding different variables constant. Because you take the partial with respect to x, you'll be holding everything but x constant. And when you take the partial with respect to y, you'll be holding different things constant. So it's pretty common to forget what you're holding constant and take the derivative wrong, and you'll get the wrong answer. So take it one step at a time, and if you get down to your gradient and you're asked to then evaluate at a certain point, then you're just putting in the values of x, y, and z at that point and evaluating what the function looks at that point and the direction in which it increases most rapidly at that very specific point. Okay, so with practice, I think you'll get the hang of it. Practice and check your steps one step at a time as you go on to the next step.